So today we'll see the topic rearrangement of terms of series. Earlier we have discussed questions on series and alternating series. So in this topic not many questions were asked, only 3 questions were asked on this topic, and one question is straight away, like they asked the proof of the Riemann rearrangement theorem. So that we'll see later. First let's discuss the basic questions that were asked on this topic. So the question 1 says that we have a series. This is a series. It is absolutely convergent series of real numbers. So they have given us a series that is summation n equals to 1 to infinity an, and it's an absolutely convergent series. Absolutely convergent, and we know that any series which is absolutely convergent is also convergent. So from here I can conclude that summation n equals to 1 to infinity an is convergent as well. And why I am able to conclude this? Because any term an is less than or equals to its modulus, so the summation is also less than or equals to its modulus. And since this is convergent, so using the comparison test I can say that this series is also convergent. So from here I concluded that this series is both convergent and absolutely convergent. Now further they have given us 2 subsequences and their sum, and we're supposed to tell what will be the sum of the entire series. So they have given us 2 subseries of the given series, and we're supposed to tell what will be the sum of entire series, and we are also supposed to give its justification, like the result that we have used in this to find out its sum. So the first they have given us that sum of all the even terms, like the terms that are occurring at even places, is 9 by 8. That means summation n equals to 1 to infinity a2n, which will give me a2 plus a4 plus a6 and so on. It is given to us as 9 by 8. And second, they have given us that the sum of the terms that are occurring at odd places is minus 3 by 8. That is summation n equals to 0 to infinity a2n plus 1, which will give me a1 plus a3 plus a5 and so on. This sum is given to us as minus 3 by 8. Now they have asked us what will be the sum of this series, that is summation n equals to 1 to infinity. That is, we are supposed to find summation n equals to 1 to infinity an. So it will be equals to, if I just expand it, it will be a1 plus a2 plus a3 plus a4 and so on, and I can write it. So this is the series I got after I expand this, and we have Riemann rearrangement theorem. So we'll be basically using Riemann rearrangement theorem that gives us flexibility to rearrange the terms of a series in whatever way we like, and based on that the sum of series changes. So I can write this series as, what I can do is I can just club in the terms that are occurring at even places and the terms that are occurring at odd places. So if I just club in the terms, it will be a1 plus a3 plus a5 and so on, plus a2 plus a4 plus a6 and so on. So I can write it as summation n equals to 1 to infinity a2n plus 1, sum varies from 0 here, plus summation n equals to 1 to infinity a2n, and I am able to write it because of Riemann rearrangement theorem. Riemann rearrangement theorem. We'll see the proof of this theorem in this video itself. So it will be equals to, since this sum is given to me as minus of 3 by 8 and this sum is given to me as 9 by 8. So the sum of series is minus 3 by 8 plus 9 by 8. That will be equals to 9 minus 3 by 8, which is 6 by 8. That is equals to 3 by 4. So the given series converges to, like the sum of the terms of the series is 3 by 4. So from here we are able to conclude that summation n equals to 1 to infinity an is equals to 3 by 4, and we are able to do this because of Riemann rearrangement theorem. So now let's move on to see the next question. So the next question says that show that the series summation 1 by n over n plus 1 is equivalent to this series. So we are supposed to show, they have given us two series and we are supposed to show that they are equivalent. So there can be many ways to show this, that they are equivalent. So one way is to show that they, like the sum of both the series is same. So we'll restore to that method only. We'll show that both the series converges to same number, and from there we can conclude that both the series are equivalent. So first let's see this series. So it is summation 1 by n plus 1, and this is a very famous series. It is called telescopic series. So it is summation n equals to 1 to infinity. So it will be equals to summation n equals to 1 to infinity. And if I use partial fraction on this term, so what I'll get is I can write it as 1 by n minus 1 by n plus 1. Because if I compute this, I'll get this only. So I've just written this term as this. Now if I just expand it, it will be 1 minus 1 by 2 plus, or what I can do is I can write it as like this: limit capital N approaches infinity, summation small n equals to 1 to capital N. So this series will become 1 by n minus 1 by n plus 1. So I can write it as limit capital N approaches infinity. If I just open the summation, so what I'll get is 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 and so on, plus 1 by capital N minus 1 minus 1 by capital N plus 1 by capital N minus 1 by capital N plus 1. Now if you observe that this term basically balances this one, this minus 1 by 2 can be balanced by this one. Likewise this minus 1 by 3 can be balanced by 1 by 3 that in the next term. Likewise this can be balanced from the previous term, and this 1 by n will be balanced by this term. So what we are left with, limit capital N approaches infinity 1 minus 1 by capital N plus 1, and if I just compute this limit, it will be equals to 1. So we got that summation n equals to 1 to infinity 1 by n times n plus 1 is equals to 1. Now if somehow we can show that the second series, that is this one, is also equals to 1, then we can conclude that both the series are basically equivalent. So let's see how we can show the second term is also equals to, second series is also equals to 1. So the second series is 1 by 2 times product from 2 to infinity 1 plus 1 by n square minus 1. Yeah, that's the second series. Now I can write it as like this: 1 by 2 limit capital N approaches infinity, product varies from 2 to capital N, because it is humanly impossible to expand it for up till infinity. So what we'll do is we'll expand it till n and then we'll check its limit. So it will be equals to 1 plus 1 by n square minus 1. So it will be equals to 1 by 2 limit capital N approaches infinity, product from small n equals to 2 to capital N. Now if I take the LCM of the inside term, it will be small n square minus 1 plus 1 divided by small n square minus 1, and this simplifies to 1 by 2 limit capital N approaches infinity, product from 2 to capital n square divided by n square minus 1, and it can be further simplified as 1 by 2 limit capital N approaches infinity, product from 2 to n square divided by n minus 1 and n plus 1. I have used a square minus b square on n square minus 1. So this is what I got. Now if I just expand it, it will be equals to 1 by 2 limit capital N approaches infinity, 2 square by 1 times 3, 3 square by 2 times 4, 4 square by 3 times 5, 5 square by 4 times 6, and so on. So second last term will be n minus 1 square by n minus 2 times n, and last term will be n square divided by n minus 1 and n plus 1. Now if we observe carefully that this 2 is balanced by the 2 in denominator in next term. Likewise 1 power of 3 is balanced by the 3 in next term, so on. If we keep on doing that, we can just balance 1 power of n minus 1 by the n minus 1 in denominator in the last term. Also, if you observe that this 3 can be balanced out by the remaining 3 that we are left with. Likewise, this 4 is balanced by this one, and this 5 is balanced by this one, and so on. So if we just keep on doing this, so we'll be left with this term. It will be equals to 1 by 2 limit capital N approaches infinity. We are left with 1 2 here, and this n will be balanced out because we can just balance it with other n in that n that will occur in the next n term, but we have taken the product till n only, so we are left with this n, and here in denominator we are left with n plus 1. Now since this 2 is a constant, so we can just pull it out of the limit, so it will be 2 by 2 limit capital N approaches infinity n divided by n plus 1, and if we just solve its limit, it will be equals to 1 limit capital N approaches infinity 1 by 1 plus 1 by capital N, and this limit is equals to 1. So we have shown that both the series, that is summation n equals to 1 to infinity 1 by n times n plus 1 is equals to 1, and the series 1 by 2 product from 2 to infinity 1 plus 1 by n square minus 1 is also equals to 1. Since both the series are equals to 1, so we can conclude that both series are convergent. Both series are equivalent, Thus both the given series are equivalent. So these are the only two questions that are asked on application part of rearrangement of terms. Now we'll see the theorem. Like this question in which they straight away asked the proof of the theorem, that is Riemann rearrangement theorem. So let's just discuss its proof. So what they have given to us is, they have given us that there is a series xn that is conditionally convergent. So conditionally convergent means that the series is convergent but it's not absolutely convergent. So that means that summation n equals to 1 to infinity xn is convergent, but it's not absolutely convergent, And further they have given us that it is a series of real numbers, and we know that real numbers can be both positive and negative. So xn, let me write it here, xn is this is not a notation of a series. I can write it as xn for all n belonging to natural number are real numbers. So from here I can conclude that xn can be either positive or negative real number. So it is like, it's not all positive series or not all negative series. It has both positive numbers and negative terms. Now they have asked us to show that there is a rearrangement possible of this series, and the rearrangement is this, such that this rearrangement basically converges to 100. So they have asked us that our claim is that we are supposed to rearrange the series, that is summation n equals to 1 to infinity xn, such that summation n equals to 1 to infinity x pi n is equals to 100. Like basically it converges to 100. This rearrangement converges to 100, and this pi has nothing to do with irrational numbers or something. It's just a notation to differentiate it from the original series that we have there. So we are supposed to show that the rearrangement that we'll do should converge to 100. So, and next time, like in upcoming exams, they can ask us to show that it converges to 1000 or some other number. So the proof is on similar lines only, and based on the number it just varies. You can do that yourself. So we'll show that how we can rearrange this series, that is summation n equals to 1 to infinity to 100. So let's move on to see the proof of this theorem. This is Riemann rearrangement theorem. Riemann rearrangement theorem. Let's move on to see its proof. So what we'll do is we'll basically see proof of Riemann rearrangement theorem. And what this Riemann rearrangement theorem states that, so Riemann rearrangement theorem. So this states that by an appropriate arrangement, a conditionally convergent series that is, let's say summation un, or let's take it as summation xn only, because in the equation they have given us xn. Summation xn can be made, the first part is made to converge to any number sigma, let's say, and in our case we are supposed to show that the sigma is 100. If we show that we can make it converge to any number sigma, then we can obviously show that it can be rearranged such that it converges to 100. That is basically a special case of this, and there are other parts as well to Riemann rearrangement theorem, but we'll see proof of the first part only, because that's the only part asked in the question. So other part is it can be made to diverge to plus infinity or to minus infinity. We can rearrange it such that it diverges to infinity or minus infinity, or we can rearrange it such that it oscillates finitely or oscillates infinitely. So we'll see only proof of this A part, that is it can be made to converge to any number sigma. So let's dive into the proof. Now if you observe that they have given us this series, that is summation xn, a series of real numbers, and it's conditionally convergent. That is also given to us in the question, conditionally convergent. Now since it is a series of real numbers, so it contains both positive and negative terms. So what we'll do is we'll define two terms. Let's name them as an and bn, which are separately, which contain separately positive and negative terms. So we are defining an as, so let's define an. So an is defined as all those terms un such that un is greater than or equals to 0, and 0 where un is less than 0. So we defined another series which contains un for all those n's where un is greater than 0, and 0 at those places where un is less than 0. And we are defining bn as minus of un where un is less than 0, and 0 where un is greater than or equals to 0. For example, if I just take a simple example to show how we define this series. So if I just take my series xn as, let's say minus 1 raised n by n. This is a conditionally convergent series. So I can take this example. So if I just write its few terms, it will be minus 1, second term will be, if this is equals to, let's say this is equals to summation un, so my u1 will be equals to minus 1 my u2 will be equals to 1 by 2, my u3 will be equals to minus 1 by 3, and u4 will be equals to 1 by 4, and so on. So how I define my an? If this is my series, my an will be 1 by 2, a1 will be basically 0, my a2 will be 1 by 2 because u2 is positive, and again u3 is negative, so it will be a3 will be 0, and again my a4 will be equals to u4 because that's positive, and so on. So my series is basically as 0 comma 1 by 2 comma 0 comma 1 by 4 comma 0 comma 1 by 6, and so on. This is how I define my an. Likewise, if I calculate bn, so from here my b1 will be u1 only, that is 1. My b2 is 0 because u2 is positive, and we have defined bn as 0 when the term in original series is greater than or equals to 0. So u2 will be 0 and u3 will be minus of that, so it will be 1 by 3, 0, 1 by 5, and so on. So this is the specific example that I took to show you how we defined an and bn. Now let's see. If you observe that the way we have defined an and bn, both these are basically series of non-negative terms. So observe that an and bn are non-negative, like an and bn both have non-negative terms. Have non-negative terms because the terms are either positive or equals to 0. That's how we defined an and bn. Now if you observe that from using these terms an and bn, I can just redefine my un. So my un will be equals to an minus bn, and if I define modulus of un, that will be an plus bn. That's how I defined, that's how I can write un using an and bn. Now in the question it is given to us that summation, okay, it is xn. Our original series is xn, so we'll just write it as xn. So I can write my xn as this and modulus of xn as this. And in the question they have given us that summation xn is conditionally convergent. That means that it is convergent but not absolutely. Convergent but not absolutely. So if that's the case, so from here I can say that summation xn, that is this, is convergent, but summation modulus of xn, that is summation an plus bn, is divergent, is not convergent, means it's divergent. So I can conclude it using the definition of conditionally convergent and how we defined xn and modulus of xn. Now if this is divergent, then at least one of an or bn should be divergent, because then only this sum is divergent. So from here we can conclude that either of summation an, or summation bn diverges. This we concluded from this part, because then only our summation an plus bn is divergent, because if both the terms are convergent, and then this summation is also convergent. Also from this term, that is summation xn is convergent, we can conclude that either both an or bn are convergent. Let me just name them, let me just name it as 1 and this as 2. So we concluded this from 2, and from 1 we can conclude that either both summation an and summation bn are convergent or both are divergent. So this we concluded from 1. Now if both of a and bn are convergent, then it is a contradiction to this that we concluded from here, like the contradiction to the previous step. So we can say that both the we can say that both summation an and summation bn diverges, because both cannot convergent, otherwise summation it will be absolutely convergent series, which is not the case because it is given to us that it is conditionally convergent. Now we have concluded all the information that can be derived from the given conditions. Now we'll show that this summation xn can be made to converge to any number sigma. So what we'll do is, since an is basically, an consists of only the positive terms, so what we can do is we can choose the least index n1. We can choose a least index n1 such that summation an from n equals to 1 to, let's say, n1 is greater than sigma, and n1 is least index. For example, if I take this series, like if let's say my n1 is, let's say, turns out to be 100, then for any n less than 100, this summation should not be greater than sigma. So n1 is the least index such that this sum turns out to be greater than sigma. Now, and I am able to choose this because since an is a positive term, like an, all the terms in an are positive, so I can find any such index such that this sum turns out to be greater than sigma. And the series consists of infinite number of terms. This n1 can be very large index as well. I'm not saying that it's restricted to 100 or 200 something. It can be any large number, maybe lakh, 10 lakh or something like that, but there will always exist some n1 such that this summation can be made greater than sigma. Likewise, I can find an index. We can find an index, let's name it as m1, such that, and this m1 index is on series bn, summation bn, m1 on summation bn such that summation n equals to 1 to n1 an minus summation, let's say, m equals to 1 to m1 bm is less than sigma. That is because bm is also a positive term series, so minus of bn, like we can just get some index m1 such that the difference of these two is less than sigma. Again, I can just, because I made the summation less than sigma, so again I can just find out another index n2 such that this sum can again be made greater than sigma. That is, if I write it again, it will be a1 plus a2 plus up till an1 minus b1 minus b2 up till minus bm1 is less than sigma. Now we can again find an index n2. We can again find an index n2, and this index n2 is again on the series summation an, n2 on an, such that this series, that is a1 plus a2 up till an1 minus b1 minus b2 minus bm1 plus an1 plus 1. I am writing it as n1 plus 1 because, like, this index n2 will be greater than this, so it will be a1 n1 plus 2 up till an1 plus n2 such that the sum is made greater than sigma. Again, for series bn, I can find another index m2 such that this sum can be made less than sigma. So again, we can find an index m2 such that m2 is on bn, m2 on summation bn such that this sum of terms, that is a1 plus a2 up till an1 minus b1 minus b2 up till minus bm1 plus an1 plus 1 plus an2 plus n1 plus 2 up till a n1 plus n2 minus b m1 plus 1 minus b m1 plus 2 up till minus b m1 plus m2 is less than sigma. And I can just keep on continuing this process. Also, if you observe that, so we can just continue, like keep on continuing this process, and we'll get many indexes like n1, n2, n3 and so on, and similarly indexes for the b series b as well. And we can just keep on continuing this process indefinitely, and we are able to do this because the series summation an and bn both are divergent series, so we are able to choose these indexes. So if you observe that, we got a rearrangement, that is, it consists of first n1 terms of a, then m1 terms of b, then n2 terms of a, and then m2 terms of b. So if you observe that, while doing this process, we are getting a series whose sequence, like we are getting another rearrangement of the original series, because a and b comes from the original series, and we are we just rearrange this term. So let's give it some name. So let's just name it as sigma n1, this as sigma n1 plus m1. Sigma n1 plus m1 is this entire thing. Likewise, if we just club it till here, it will be sigma n1 plus m1 plus n2, and if we just club in all the four terms, it will be sigma n1 plus n2 m1 plus n2 plus m2, and so on. We can just proceed it. It will give us a sequence of partial sum. So we got another rearrangement. Let's name it as summation maybe vn is rearranged series, and sigma n is basically sequence of partial sum, is its sequence of partial sum. So if you observe that, we got our sigma n1 as greater than sigma, then sigma n1 plus m1 is less than sigma, and again sigma n1 plus m1 plus n2 greater than sigma, and sigma n1 plus m1 plus n2 plus m2 less than sigma, and so on. That's how we got. So we got a series such that we got a series sigma n which converges to basically sigma, because one moment it is greater than sigma, some sequence of partial sum is greater than sigma, and another moment it is less than sigma. So we can just use the sandwich result here, which shows that the rearrangement basically summation vn converges to sigma. Now if we just plug in 100 at place of sigma in this proof, we can conclude that the given series can be rearranged to converge to a number 100 or any other number. You can place any other number at place of sigma. So that completes the proof of Riemann rearrangement theorem. Also, one more thing, like in the first question that we discussed today, we are able to rearrange it, and conclude its sum because of this Dirichlet theorem, which says that a series obtained from absolutely convergent series by the rearrangement of terms converges absolutely. So since summation an is absolutely convergent, so the series that we get after its rearrangement is also absolutely convergent. If this is absolutely convergent, and using Dirichlet theorem, we concluded that the rearrangement, that is sum of all the odd terms and all the even terms, this rearrangement is also absolutely convergent. And further, Dirichlet theorem says that they both converges to the same sum as the original series. So the original series will also converge to the same sum as the sum of these two sub-series. So because of that, we are able to conclude that the original series converges to 3 by 4. So the justification here is Dirichlet's theorem. Dirichlet's theorem on rearrangement of terms. Rearrangement of terms of series, and you can also check out its proof in SC Malik and Savita Arora. SC Malik and Savita Arora book on mathematical analysis. So that's all for today. We'll discuss next topic in next video. Thank you for watching.